So, beginning to talk about advanced single area OSPF configuration, the first thing we have to do is talk about all the different kinds of networks that you can deploy OSPF into. And the serial lanes that we've used so far are just the tip of the iceberg. There are 5 of them, in point of fact. There's your standard point-to-point network. This is what we've been doing with our, if you think about the topologies we've been using since the beginning of Chapter 8, those 3 routers in a ring with serial lines between them. Fully meshed, 3 edges, 3 vertices, and there's no need for a BR, DR, or BDR. Every router has an adjacency to every other router. The other option, which we're going to start playing with now, is our broadcast multi-access network. Essentially, using an Ethernet LAN, an Ethernet segment to tie routers to each other. Not so that they're not point-to-point with each other, but they're cooperating through a switch. Now, this doesn't, you wouldn't initially think, why would we do this? Think back to first hop redundancy protocols, HSRP. What if, and now the HSRP implementations we did were fairly simple. You've got 2 physical routers cooperating to present 1 virtual router to the subnet they're supporting. What if you had a lot of hosts on that subnet, or you had an absolute need for perfect uptime, and you had not just one set of switches going from your access layer through your distro into your core? What if you had a bunch of switches, a bunch of routers, and you had 4 or 5 routers feeding into that subnet so that you couldn't possibly lose connectivity to it? 4 or 5 routers through a handful of different switches, possibly, and if you're doing that, you might actually have ether channel coming from the host to the switch, what we would call NIC teaming, all that kind of thing. You might really actually need a broadcast multi-access configuration. There's also the non-broadcast multi-access configuration, NBMA. The main example here is a frame relay. So you've got your routers tied into a frame relay network, and they all have to peer to each other somehow. Then also you got your point to multipoint. You may have a frame relay with kind of a hub and spoke topology, so that your hubs are all talking to that. Your spokes are all talking to that hub location. And then finally, you've got virtual networks. It's a special OSPF network used to connect truly distant OSPF areas through the backbone. And if it's really, really unusual, you might actually have, for lack of a better word, an intermediary backbone, a sub-backbone. Because as you can see in this image here, you've got your area 0, which would usually be your backbone. And what if there's a whole bunch of stuff over on the other end, so that this really is the backbone? And you've got your area 51, no little green men involved. And then you've got this backbone in the middle, which is obviously a backbone, but it's not area 0. And as we know, area 0 is the backbone, period, full stop. But if you have to build some kind of virtual link between point A and point B, then maybe there's a subsidiary backbone. We might see this again later with GRE tunneling and connecting networks. So let's talk about the kind of challenges that these multi-access networks present us with. And we've referenced this before, talk about why you have to have a controlled approach to peer and neighbor relationships in a multi-access network, because the math gets out of hand quickly. So hold on. So as we know, neighbor adjacencies get difficult in a hurry. With 3 routers, 3 switches, 2 neighbor adjacencies for each router, no problem. 4 routers all mesh together. Now, the key thing here is that each of these routers is in a full mesh. That is, every router tied to every other router. Every point, every vertex, if we're thinking in terms of graph theory here, and we really do have to think about graph theory because that's kind of where the SPF algorithm came from in the first place, is applied mathematics. If every router is talking to every other router, and every router has to have a neighbor adjacency with every router that it's talking to, 4 routers gives you 6 adjacencies. Not too bad. 5 routers gives you 10. 10 gives you 45, and we're starting to get a little nuts here. 20 gives you 120. 50 gives you 1200. You'd spend all your time establishing neighbor relationships and exchanging LSAs, and no. So that's one problem, establishing all those neighbor adjacencies. The more significant problem is all those LSAs flooding out through the network back and forth that everyone has to talk to, everybody has to hear from everybody else, compute all the possible paths. Because of course, with OSPF, the definition of convergence is everybody has the same link state database. They don't all have the same SPF tree. They don't all have the same routing table, but they do all have the same map of their common topology. And if they have to spend all their time doing that, when are they going to route traffic for their end users? So the solution here is to pick one. Pick someone to be in charge of that broadcast multi-access network, so that everybody becomes a neighbor with the IT person. So we call this the IT router, the DR, the designated router. OSPF will realize that it is in a multi-access network. I mean, you don't have to tell OSPF that, oh, by the way, this is an Ethernet LAN. It will notice that right off the bat and do the work for you, even if you don't do anything. So with some of our labs, if we had, in Chapter 9, if we had been in the lab, truly and physically, we would actually have crossed this bridge a little bit early. Because some of our labs are implemented not with serial lines, but with Ethernet. And so, anyway, what happens is it elects a DR. It elects a BDR, backup designated router, in case the DR falls off the network. Then everyone sends their LSAs to it. Everybody makes their neighbor adjacency with it. And it is in charge of sending LSAs for that whole area to the rest of the network. So only the DR is producing LSAs for everyone that it is representing. It becomes like a delegate to Congress, shall we say. So it speaks for the group speaks to it speaks for the group, and so there's everyone is still in some kind of neighbor relationship. All of their states are still being represented to the wider network, but they're not all doing the work for themselves. Now, in terms of verifying this, there's a couple of different ways to do this. So the simplest way to do this is show IP OSPF interface. If you do this with show IP OSPF interface, you'll see in the green here the designated router, the backup designated router, its state, and its priority. The priority 1 is your default priority. And of course, we could do all of this for OSPF v3 and IPv6 by replacing IP with IPv6. So in this case, because the DR is elected on the basis of router ID, whereas in a spanning tree network, the election is done on the basis of hardware address, layer 2 information. This is a layer 3 network, so everything is done on layer 3 terms. The highest router ID wins. In this case, 3.3.3 is higher than 2.2.2 and 1.1.1, so it wins. So if there's a stated router ID, that wins. If there's not a stated router ID, it'll use a loopback or a physical address in that network. Now, the thing here is, and you might see this on tests and things, you can these routers are actually in multiple networks simultaneously. if OSPF knows about 2.0 and the 192.168.1.0 and the 1.0 over here and the 3.0 over here, there's going to be a BRDR election process for this here and over here and over here and over there. Each Ethernet network is going to get a DR election, even if we're talking about an interface that's going down into the access layer that doesn't have a router on the other side of that switch. It is still going to do that. And we actually kind of saw that in a previous lab. If you looked at the state of that gigabit network that you used for, say, talking to a virtual PC in the lab, you would have seen that that gigabit interface has a DR state. It's all by itself, but being all by itself, it decides that it's it. So the thing to note here is that because we're talking about Ethernet networks, it may be in multiple BRDR states, depending on where it is. The election that you need to think about is the one that is relevant to this address in here. So this address out here isn't relevant while this router ID is in place. As soon as this router ID is in place, the IP addresses in here become relevant because 192.168 is larger than 172.16.0.0. So there's that. We can also look at these adjacencies with show IP OSPF neighbor, like this. Your routers will be in one of the following states: full DR if it is fully converged and the designated router. Full BDR if it is fully converged and it's the backup designated router. Full DR other if it is fully converged and neither the backup nor the designated router. And then two-way DR other, which is also valid. Okay, so and then the election process, as we've noted, works on the basis of two things: the stated priority on that interface, and the stated priority on that interface will take effect over the router ID. So if you want the device with the lowest router ID to win the DR election, you absolutely have to put a priority value on the interface facing into that network. Going back to our topology for a minute, from this topology here, if I put a priority value over here on gig 01 of 255, of course that's completely pointless because it's going down into an access layer network. A priority value 255 over here on gig 01 has no relevance whatsoever to 192.168.10/28. The priority value would have to be in here, in this Ethernet segment, for it to do any good. The highest priority wins the election. The second highest priority becomes the backup designated router. The default priority value is 1. A priority value of 255 will always win the election. The priority value of 0 will never really compete. Like a candidate who always runs for office and never wins. Now, if priority values are equals, then router IDs become the key concern. So there's a order of precedence within the order of precedence. So first, priority value. Highest priority value wins. If all the priority values are equal, then we fall over to router ID. And of course, the router ID order of precedence that we know about takes effect. Manually configured, loopbacks, physical addresses. One last thing to note, these elections are not preemptive. If the DR falls off the network and pops back on, it will come back into a DR other state. It will only win the election again unless the BDR also falls off the network and it has to go looking for a new set of a new designated router. And then, of course, our priority values. And you can change your priority value with the priority value command. But of course, that won't take effect until you reboot everything, clear the process, reboot the routers, etc. Next, we'll talk about default route propagation.